Reverse Engineering for Everyone by My Techno Talent. Read by Mr. Fresh. Part 1. Goals. Wait, what's reverse engineering? Wikipedia defines it as reverse engineering, also called backwards engineering or back engineering, is the process by which an artificial object is deconstructed to reveal its designs, architecture, code, or to extract knowledge from the object. It is similar to scientific research, the only difference being that scientific research is conducted in a natural phenomenon. Whew, that was quite a mouthful, wasn't it? Well, it is one of the main reasons why this tutorial set exists, to make reverse engineering as simple as possible. This comprehensive set of reverse engineering tutorials covers x86, x64, as well as 32-bit ARM and 64-bit architectures. If you are a newbie looking to learn reversing, or just someone looking to revise on some concepts, you're at the right place. As a beginner, these tutorials will carry you from nothing up to the mid-basics of reverse engineering, a skill that everyone within the realm of cybersecurity should possess. If you're here just to refresh some concepts, you can conveniently use the sidebar to take a look at the sections that have been covered so far. So can you get the entire tutorial set in PDF or MOBI format? Yes. All these ebook versions will get updated automatically as new tutorials will be added. The x86 architecture. Let's dive in right away. Part 1. Goals. Essential to the discussion of basic reverse engineering is the concept of modern malware analysis. Malware analysis is the understanding and examination of information necessary to respond to a network intrusion. This short tutorial will begin with the basic concepts of malware reverse engineering and graduate to an entry-level basic examination of assembly language. The keys to the kingdom, so to speak, are rooted in the breakdown of the respective suspected malware binary and how to find it on your network and ultimately to contain it. Upon full identification of the files required for deeper analysis, it is critical to develop signatures to detect malware infections throughout your network, whether it be a home-based LAN or complex corporate WAN, to which malware analysis is necessary to develop host-based and network signatures. To begin with the concept of a host-based signature, we need to understand that these are utilized to find malicious code in a target machine. Host-based signatures are also referred to as indicators, which can identify files created or edited by the infected code, which can make hidden changes to a computer's registry. This is quite in contrast with antivirus signatures, because these concentrate on what the malware actually does rather than the makeup of the malware, which makes them more effective in finding malware that can migrate or has been removed from the media. In contrast, network signatures are used to find malicious code by examining network traffic. It is important to note such tools as Wireshark and the like are often effective in such analysis. Upon identification of these aforementioned signatures, the next step is to identify what the malware is actually doing. In our next lesson, we will discuss techniques of malware analysis. Part 2. Techniques. There are two basic techniques that you can employ when analyzing malware. The first being static analysis and the other being dynamic analysis. Static analysis uses software tools to examine the executable without running the actual decompiled instructions in assembly. We will not focus on this type of analysis here, as we are going to focus on actual disassembled binaries instead. However, in future courses we will. Dynamic analysis uses disassemblers and debuggers to analyze malware binaries while actually running them. The most popular tool in the market today is called IDA, which is a multi-platform, multi-processor, disassembler, and debugger. There are other disassembler debugger tools as well on the market today, such as Hopper Disassembler, OllyDebug, or OllyDBG, and many more. A disassembler will convert an executable binary written in assembly, C, C++, etc., into assembly language instructions that you can debug and manipulate. Reverse engineering is much more than just malware analysis. At the end of our series, our capstone tutorial will utilize IDA, as we will create a real-world scenario where you will be tasked by the CEO of ABC Biochemicals to secretly try to ethically hack his company's software that controls a bulletproof door in a very sensitive biochemical lab in order to test how well the software works against real threats. The project will be very basic, however, it will ultimately showcase the power of assembly language and how one can use it to reverse engineer and ultimately provide solutions on how to better design the code to make it safer. In our next lesson, we will discuss various types of malware. Part 3. Types of malware. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Malware falls into several categories, of which I will touch briefly upon below. A backdoor is malicious code that embeds itself into a computer to allow a remote attacker access with very little or sometimes no authority to execute various commands on any respective local computer. A botnet allows an attacker access to a system, however, receives instructions not from one remote attacker but from a command and control server, to which can control an unlimited amount of computers at the same time. A downloader is nothing more than malicious code that has only one purpose, which is to install other malicious software. Downloaders are frequently installed when a hacker gains access to a system initially. The downloader then installs additional software to control the system. We find information access malware, which gathers information from a computer and sends it directly to a host, such as a keylogger or password grabber, and usually used to obtain access to various online accounts that can be very sensitive. There are malicious programs that launch other malicious programs which use non-standard options to get increased access or a greater cloaking, hiding technique when penetrating a system. One of the most dangerous forms of malware is the rootkit, which hides the existence of itself and additional malware from the user, which makes it extremely hard to locate. A rootkit can manipulate processes such as hiding their IP in an IP scan so that a user may never know that they have a direct socket to a botnet or other remote computer. Scareware is used to trick a user into purchasing additional software to falsely protect a user when there is no real threat whatsoever that exists. Once a user pays to have the tricked software removed from the computer, it can then stay resident and later emerge in an altered form. There are also various kinds of malware that send spam from a target machine, which generates income for the attacker by allowing them to sell various services to other users. The final form of malware that is of a traditional worm or virus, which copies itself and goes after other computers. This is the end of the road for now regarding our discussion of malware, because we first need to go back to the beginning and understand how a computer works at its base level. In our next lesson, we will begin our journey into x86 assembly language. In order to truly understand the very basics of reverse engineering and malware, we need to cover the next several months to take a deep dive into the core and build our way up. Part 4, x86 Assembly Intro. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Ladies and gentlemen, boys and girls, children of all ages, we are about to embark on a journey that will change your life forever. There is a vast material to cover to get a good understanding of assembly language and why it is important to understand the basics. The first question we must answer is, what is x86 assembly language? To which the answer is a family of backward compatible assembly languages which provide compatibility back to the Intel 8000 series of microprocessors. x86 assembly languages are used to produce object code for the aforementioned series of processors. It uses mnemonics to represent the instructions that the CPU can execute. Assembly language for the x86 microprocessor works in conjunction with various operating systems. We will focus on Linux assembly language utilizing the Intel syntax, in addition to learning how to program in C, to which we will disassemble the source code and analyze the respective assembly. x86 assembly language has two choices of syntax. The AT&T syntax was dominant in the Unix world since the OS was developed at AT&T Bell Labs. In contrast, the Intel syntax was originally used for the documentation of the x86 platform and was dominant in the MS-DOS and Windows environments. For our purposes, when we are ultimately disassembling and debugging software, whether it be in a Linux or Windows environment, we will see the Intel syntax in large measure. This is essential whether we are examining a Windows binary in PE format or a Linux binary in ELF format. More on that later in this tutorial. The main differences between the two is in the AT&T syntax, the source comes before the destination, and in the Intel syntax, the destination comes before the source. We will discuss this in more detail later in the tutorial. Before you run for the door and regret embarking on this journey, remember some basic context helps to which we will develop throughout our quest. Many of these topics may be confusing at this point, which is perfectly normal, as we will develop them in time. We will focus on Linux assembly because Linux runs on a variety of hardware and is capable of running devices such as a cell phone, personal computer, or a complex commercial server. Linux is also open source, and there are many versions. We will focus on Ubuntu in our demonstrations, which can be freely obtained. In contrast, the Windows operating system is owned and controlled by one company, Microsoft, to which all updates, security patches, and service patches come directly from them, where Linux has millions of professionals providing the same absolutely free. We will also focus on a 32-bit architecture, as ultimately most malware will be written for such in order to infect as many systems as possible. 32-bit applications, malware, will work on 64-bit systems, so we want to understand the basics of the 32-bit world. In our next lesson, we will discuss the binary number system. Grab your cup of coffee, you are going to need it. Part 5, Binary Number System. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Binary numbers are what define the core of a computer. A bit within a computer is either on or off. A bit has either electricity turned on to it or it is absent of such. We will dive into this deeper in future tutorials. Puzzled and confused? Where do we go from here? Have no fear. The binary number system is here. It is important to understand that in binary, each column has a value 2 times the column to its right, and there are only 2 digits in the base, which happen to be 0 and 1. In decimal, base 10, say we have the number 15, which means 1 times 10 plus 5 times 1 equals 15. Therefore, the 5 is the number times 1, and the 1 is that number times 10. Binary works in a similar fashion. However, we are now referring to base 2. That same number in binary is 1111. To illustrate, you can look at this picture. Binary numbers are important because using them instead of the decimal system simplifies the design of computers and related technologies. The simplest definition of the binary number system is a system of numbering that uses only 2 digits, as we mentioned above, to represent numbers necessary for a computer architecture rather than using the digits 1 through 9 plus 0 to represent such. In our next lesson, we will discuss the hexadecimal number system. It only gets more exciting from here. Part 6. Hexadecimal number system. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Now that we are binary masters, it's time to tackle the numbering system of numbering systems. We learned in binary that each number represents a bit. If we combine 8 bits, we get a byte. A byte can be further subdivided into its top 4 bits and its low 4 bits. A combination of 4 bits is a nibble. Since 4 bits gives you the possible range from 0 to 15, a base 16 number system is easier to work with. Keep in mind, when we say base 16, we start with 0, and therefore 0 to 15 is 16 different numbers. This exciting number system is called hexadecimal. The reason why we use this number system is that in x86 assembly, it is much easier to express binary number representations in hexadecimal than it is in any other numbering system. Hexadecimal is similar to every other number system, except in hexadecimal, each column has a value of 16 times the value of the column to its right. The fun part about hexadecimal is that not only do we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we have A, B, C, D, E, and F. Therefore, 16 different symbols. Let's look at a simple table to see how hexadecimal compares to decimal. See this table. Okay, I see the smoke coming out of your ears, but it's okay. In decimal, everything is dealt with in the power of 10. Let's take the number 42 and examine it in decimal. Remember, 10 to the 0 power is 1, and 10 to the first power is 10. Therefore, 2 plus 40 equals 42. Grab your coffee. Here comes the fun stuff. If we understand that decimal is a base 10 number system, we can create a simple formula where B represents the base. In this case, B equals 10. In binary, 42 decimal is 00101010, binary as follows. In hexadecimal, everything is dealt with in the power of 16. Therefore, 42 in decimal is 2a in hexadecimal. This is the same as saying C table. Keep in mind, 10 decimal is equal to a hexadecimal and 2 decimal is equal to 2 hexadecimal. In our formula above, when we deal with A, B, C, D, E, or F, we need to convert them into their decimal equivalent. Let's take another example of F5 hexadecimal. This would be as follows. Let's look at a binary to hexadecimal table. It is important to understand that every hexadecimal number is 4 bits long, or called a nibble. This will become critical when we are reverse engineering our C programs into assembly. Let's look at this another way. Let's work with some more hexadecimal numbers and convert them to decimal. To re-emphasize F1 CD as a simple conversion, D is 13 times 1 equals 13, C is 12 times 16 equals 192, 1 is 1 times 256 equals 256, F is 15 times 4096 equals 61,440, 13 plus 192 plus 256 plus 61,440 equals 61,901. Addition in hexadecimal works as follows. From this point forward, all numbers in hexadecimal will have a H next to the number. You are probably asking yourself, why is this guy spending so much time going over so many different ways of learning this? The answer is that each of us learn a little different from the next. I wanted to show several representations of hexadecimal compared to decimal and binary to help put together the whole picture. It is fundamental that you understand what is going on here in order to proceed any further. If you have any questions, please comment below and I will be more than happy to help. In our next lesson, we will discuss switches, transistors, and memory. Part 7, Transistors and Memory. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. In our last lesson, we took a very deep dive into the hexadecimal number system. I am going to keep this week's lesson short so that you can reread last week's lesson. I cannot emphasize how important it is to understand hexadecimal number conversions in addition to the ability to manually add and subtract them. In the real world, we have calculators. In the real world, we use the Windows operating system. In the real world, professional reverse engineers use GUI debuggers like IDA Pro and others. The question is, why am I not jumping right into the core of what real reverse engineers do? The answer is simple. One must have a deep respect and understanding of the machine in order to become great. We will never change the world without fully understanding it first. Patience and perseverance win the day. I focus on Linux and console-based programming because most professional servers utilize Linux, and therefore is the greatest threat of malware. Understanding Linux assembly allows you to very easily grasp the library choking portable executable format of Windows assembly in a much deeper way. As I step off the soapbox, let's get back to the basics of computers. So here we go. When we ask ourselves, what is a computer, one must go down to about as basic as one can get. Electronic computers are simply made out of transistor switches. Transistors are microscopic crystals of silicon that use electrical properties of silicon to act as switches. Modern computers have what are referred to as field effect transistors. Let's use an example of 3 pins. When an electrical voltage is applied to pin 1, current then flows between pins 2 and 3. When the voltage is removed from the first pin, current stops flowing between pins 2 and 3. When we zoom out a bit, we see that there are also diodes and capacitors. When taken together with the transistor switches, we now have a memory cell. A memory cell keeps a minimum current flow to which, when you put a small voltage on its input pin and a similar voltage on its select pin, a voltage will appear and remain on its output pin. The output voltage remains in its set state until the voltage is removed from the input pin in conjunction with the select pin. Why is this important, you ask? Very simply, the presence of voltage indicates a binary 1, and the absence of voltage indicates a binary 0. Therefore, the memory cell holds one binary digit or bit, which is either 1 or 0, meaning on or off. In our next lesson, we will discuss bytes and words. Part 8. Bytes, words, double words, etc. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Memory is measured in bytes. A byte is 8 bits. 2 bytes are called a word, and 2 words are called a double word, which is 4 bytes, 32-bit, and a quad word is 8 bytes, 64-bit. A byte is 8 bits and is 2 to the 8th power, which is 256. The number of binary numbers, 8 bits in size, is one of 256 values starting at 0 and going to 255. Every byte of memory in a computer has its own unique address. Let's review the disassembled instructions for a simple Hello World application in Linux by setting a breakpoint on the main function. We will use the GDB debugger. Don't worry if this does not make sense yet. The point of utilizing this example is to give you a sneak peek into our first program that we will examine in addition to learning about memory in a computer. Below is an examination of the ESP register. Again, it is not critical that you understand what a register is or what ESP does. We simply want to see what a memory location looks like. We see the memory location at 0xFFFFD040, which of course is in hexadecimal. We also see the value inside the ESP register, which is 0xF7FAC3DC, which is also in hexadecimal. It is important to understand that 0xFFFFD040 is 4 bytes and is a double word. As we learned in Part 6, hexadecimal number system, Each hexadecimal digit is 4 bits long, otherwise called a nibble. In 0xFFFFD040, let's look at the rightmost digit of 0. In this example, 0 hexadecimal is 4 bits long. If we look at 40 in hexadecimal, we see that is a byte in length or 8 bits long. If we look at D040, we have 2 bytes or a word in length. Finally, FFFFD040 is a double word or 4 bytes in length, which is 32 bits long. The 0x at the beginning of the address just designates that it is a hexadecimal value. A computer program is nothing more than machine instructions stored in memory. A 32-bit CPU fetches a double word from a memory address. A double word is 4 bytes in a row, which is read from memory and loaded into the CPU. As soon as it finishes executing, the CPU fetches the next machine instruction in memory from the instruction pointer. Those of you new to assembly have now had your first look. Don't get discouraged or frustrated if you do not know what is going on here. We will take our time and go through dozens of examples to break down each step in future lessons. What is important is that you take your time and examine what each lesson is discussing. Please always feel free to comment below with any questions. In our next tutorial, we will discuss the basics of x86 architecture. Part 9, x86 Basic Architecture. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. A computer application is simply a table of machine instructions stored in memory to which the binary numbers which make up the program are unique only in the way the CPU deals with them. The basic architecture is made up of a CPU, memory, and I/O devices, which are input-output devices, which are all connected by a system bus as detailed below. The CPU consists of 4 parts, which are 1. The control unit, which retrieves and decodes instructions from the CPU and then storing and retrieving them to and from memory. 2. The execution unit, where the execution of fetching and retrieving instructions occurs. 3. Registers, internal CPU memory locations used as a temporary data storage. And 4. Flags, which indicate events when execution occurs. We will discuss 32-bit x86, so therefore a 32-bit CPU first fetches a double word, 4 bytes or 32 bits in length, from a specific address in memory and is read from memory and loaded into the CPU. At this point, the CPU looks at the binary pattern of bits within the double word and begins executing the procedure that the fetched machine instruction directs it to do. Upon completion of executing an instruction, the CPU goes to memory and fetches the next machine instruction in sequence. The CPU has a register, which we will discuss registers in a future tutorial, called the EIP or instruction pointer, that contains the address of the next instruction to be fetched from memory and then executed. We can immediately see that if we controlled flow of EIP, we can alter the program to do things it was not intended to do. This is a popular technique upon which malware operates. The entire fetch and execute process is tied to the system clock, which is an oscillator that emits square wave pulses at precise intervals. In our next tutorial, we will dive deeper into the IA32 architecture with a discussion of the general purpose registers. Part 10. General purpose registers. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. The general purpose registers are used to temporarily store data as it is processed on the processor. The registers have evolved dramatically over time and continue to do so. We will focus on 32-bit x86 architecture for our purposes. Each new version of general purpose registers is created to be backward compatible with previous processors. This means that code utilizing 8-bit registers on the 8080 chips will still function on today's 64-bit chipset. General purpose registers can be used to hold any type of data to which some have acquired specific use, which are used in programs. Let's review the 8 general purpose registers in an IA32 architecture. EAX. Main register used in arithmetic calculations, also known as accumulator, as it holds results of arithmetic operations and function return values. EBX. The base register, pointer to data in the DS segment, used to store the base address of a program. ECX, the counter register, is often used to hold a value representing the number of times a process is to be repeated, used for loop and string operations. EDX, a general purpose register, additionally used for I/O operations. In addition, will extend EAX to 64 bits. ESI, Source Index Register, pointer to data in the segment pointed to by the DS register, used as an offset address in string and array operations. It holds the address from where to read data. EDI, Destination Index Register, pointer to data or destination in the segment pointed to by the ES register, used as an offset address in string and array operations. It holds the implied write address of all string operations. EBP, base pointer, pointer to data on the stack in the SS segment. It points to the bottom of the current stack frame. It is used to reference local variables. ESP, stack pointer in the SS segment. It points to the top of the current stack frame. It is used to reference local variables. Keep in mind, each of the above registers are 32-bit in length or 4 bytes in length. Each of the lower 2 bytes of the EAX, EBX, ECX, and EDX registers can be referenced by AX and then subdivided by the names AH, BH, CH, and DH for high bytes, and AL, BL, CL, and DL for the low bytes, which are 1 byte each. In addition, the ESI, EDI, EBP, and ESP can be referenced by their 16-bit equivalent, which is SI, DI, BP, SP. This can be a bit confusing to someone who has not studied computer engineering. However, let me illustrate in the table below. EAX would have AX as its 16-bit segment, and then you can further subdivide AX into AL for the low 8 bits and AH for the high 8 bits. The same holds true for EBX, ECX, and EDX as well. EBX would have BX as its 16-bit segment, and then you can further subdivide BX into BL for the low 8 bits and BH for the high 8 bits. ECX would have CX as its 16-bit segment, and then you can further subdivide CX into CL for the low 8 bits and CH for the high 8 bits. EDX would have DX as its 16-bit segment, and then you can further subdivide DX into DL for the low 8 bits and DH for the high 8 bits. ESI, EDI, EBP, and ESP can be broken down into its 16-bit segments as follows. ESI would have SI as its 16-bit segment, EDI would have DI as its 16-bit segment, EBP would have BP as its 16-bit segment, and ESP would have SP as its 16-bit segment. In our next tutorial, we will continue our discussion of the IA32 architecture with the segment registers. Part 11. Segment registers. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. The segment registers are used specifically for referencing memory locations. There are 3 different methods of accessing system memory, of which we will focus on the flat memory model, which is relevant for our purposes. There are 6 segment registers, which are as follows. CS, Code Segment Register, stores the base location of the code section. .txt or .text section, which is used for data access. DS, Data Segment Register, stores the default location for variables. .data section, which is used for data access. ES, Extra Segment Register, which is used during string operations. SS, Stack Segment Register, stores the base location of the stack segment and is used when implicitly using the stack pointer or when explicitly using the base pointer. FS, Extra Segment Register. GS, Extra Segment Register. Each segment register is 16 bits and contains the pointer to the start of the memory-specific segment. The CS register contains the pointer to the code segment in memory. The code segment is where the instruction codes are stored in memory. The processor retrieves instruction codes from memory based on the CS register value and an offset value contained in the instruction pointer, EIP, register. Keep in mind, no program can explicitly load or change the CS register. The processor assigns its values as the program is assigned a memory space. The DS, ES, FS, and GS segment registers are all used to point to data segments. Each of the 4 separate data segments can help the program separate data elements to ensure that they do not overlap. The program loads the data segment registers with the appropriate pointer value for the segments and then reference individual memory locations using an offset value. The stack segment register, SS, is used to point to the stack segment. The stack contains data values passed to functions and procedures within the program. Segment registers are considered part of the operating system and can neither read nor be changed directly in almost all cases. When working in the protected mode flat model x86 architecture, which is 32-bit, your program runs and receives a 4 GB address space to which any 32-bit register can potentially address any of the 4 billion memory locations except for those protected areas defined by the operating system. Physical memory may be larger than 4 gigabytes. However, a 32-bit register can only express 4,294,967,296 different locations. If you have more than 4 gigabytes of memory in your computer, the OS must arrange a 4 gigabyte region within memory, and your programs are limited to that new region. This task is completed by the segment registers, and the OS keeps close control over this. In our next tutorial, we will continue our discussion of the IA32 architecture with the instruction pointer register. Part 12, Instruction Pointer Register. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. The instruction pointer register, called the EIP register, is simply the most important register you will deal with in any reverse engineering. The EIP keeps track of the next instruction code to execute. EIP points to the next instruction to execute. If you were to alter that pointer to jump to another area in the code, you have complete control over that program. Let's jump ahead and dive into some code. Here is an example of a simple Hello World application in C that we will go into more detail much later in our tutorial series. For our purposes today, we will see the raw power of assembly language, and particularly that of the EIP register, and what we can do to completely hack program control. Don't worry if you do not understand what it does or its functionality. What to take note of here is the fact we have a function called unreachable function that is never called by the main function. As you will see, if we can control the EIP register, we can hack this program to execute that code. We have simply compiled the code to work with the IA32 instruction set and ran it. As you can see, there is no call to the unreachable function of any kind, as it is unreachable under normal conditions, as you can see the Hello World printed when executed. We have disassembled the program using the GDB debugger. We have set a breakpoint on the main function and ran the program. The equal sign and right redirector operator shows where EIP is pointing to when we step to the next instruction. If we follow normal program flow, Hello World will print to the console and exit. If we run the program again and do an examination of where EIP is pointing to, we will see. We can see EIP is pointing to main plus 17, or the address of 0x680CEC83. Let's examine the unreachable function and see where it starts in memory and write down that address. The next step is to set EIP to address 0x080484-3B so that we can hijack program flow to run the unreachable function. Now that we have hacked control of EIP, let's continue and watch how we have hijacked the operation of a running program to our advantage. Ta-da! We have hacked the program. So the question in your mind is, why did you show me this when I have no idea of what any of this is? It is important to understand that when we are doing a lengthy tutorial such as this, we should sometimes look forward to see why we are taking so many steps to learn the basics before we dive in. It is important, however, to show you that if you stay with the tutorial, your hard work will pay off, as we will learn how to hijack any running program to make it do whatever we want, in addition to proactively breaking down a malicious program so that we can not only disable it, but trace it back to a potential IP of where the hack originated. In our next tutorial, we will continue our discussion of the IA32 architecture with the control registers. Part 13, Control Registers. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. There are 5 control registers, which are used to determine the operating mode of the CPU and the characteristics of the current executing task. Each control register is as follows. CR0, system flag, that controls the operating mode and various states of the processor. CR1, not currently implemented. CR2, memory page fault information. CR3, memory page directory information. CR4, flags that enable processor feathers and indicate feature capabilities of the processor. The values in each of the control registers can't be directly accessed. However, the data in the control register can be moved to one of the general purpose registers, and once the data is in a GP register, a program can examine the bit flags in the register to determine the operating status of the processor in conjunction with the current running task. If a change is required to a control register flag value, the change can be made to the data in the GP register and the register moved to the CR. Low-level system programmers usually modify the values in control registers. Normal application programs do not usually modify control register entries. However, they might query flag values to determine the capabilities of the host processor chip on which the program is currently running. In our next tutorial, we will continue our discussion of the IA32 architecture with the topic of flags. Part 14, Flags. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. The topic of flags are one of the most extremely complex and complicated concepts of assembly language and program flow control when reverse engineering. This information will become much clearer as we enter into the final phase of our training when we reverse engineer C applications into assembly language. What is important here is to take away the fact that flags help control, check, and verify program execution and are a mechanism to determine whether each operation that is performed by the processor is successful or not. Flags are critical to assembly language applications as they are a check to verify each program function's successful execution. We are dealing with 32-bit assembly to which a single 32-bit register which contains a group of status, control, and system flags exists. The register is called the eFlags register as it contains 32 bits of information that are mapped to represent specific flags of information. There are 3 kinds of flags, which are status flags, control flags, and system flags. Status flags are as follows: CF, carry flag; PF, parity flag; AF, adjust flag; ZF, zero flag; SF, sign flag; OF, overflow flag. The carry flag is set when a math operation on an unsigned integer value generates a carry or borrow for the most significant bit. This is an overflow condition for the register involved in the math operation. When this occurs, the remaining data in the register is not the correct answer to the math operation. The parity flag is used to indicate corrupt data as a result of a math operation in a register. When checked, the parity flag is set if the total number of 1 bits in the result is even and is cleared if the total number of 1 bits in the result is odd. When the parity flag is checked, an application can determine whether the register has been corrupted since the operation. The adjust flag is used in binary coded decimal math operations and is set if a carry or borrow operation occurs from bit 3 of the register used for the calculation. The 0 flag is set if the result of an operation is 0. The sign flag is set to the most significant bit of the result, which is the sign bit, and indicates whether the result is positive or negative. The overflow flag is used in signed integer arithmetic when a positive value is too big or a negative value is too small to be represented in the register. Control flags are utilized to control specific behavior in the processor. The DF flag, which is the direction flag, is used to control the way strings are handled by the processor. When set, string instructions automatically decrement memory addresses to get the next byte in the string. When cleared, string instructions automatically increment memory addresses to get the next byte in the string. System flags are used to control OS level operations, which should never be modified by any respective program or application. TF trap flag, IF interrupt enable flag, IOPL IO privilege level flag, NT nested task flag, RF resume flag, VM virtual 8086 mode flag, AC alignment check flag, VIF virtual interrupt flag, VIP virtual interrupt pending flag, ID identification flag. The trap flag is set to enable single step mode, and when in this mode the processor performs only one instruction code at a time, waiting for a signal to perform the next instruction. This is essential when debugging. The interrupt enable flag controls how the processor responds to signals received from external sources. The IO privilege field indicates the input-output privilege level of the currently running task and defines access levels for the input-output address space, which must be less than or equal to the access level required to access the respective address space. In the case where it is not less than or equal to the access level required, any request to access the address space will be denied. The nested task flag controls whether the currently running task is linked to the previously executed task and is used for chaining interrupted and called tasks. The resume flag controls how the processor responds to exceptions when in debugging mode. The VM flag indicates that the processor is operating in virtual 8086 mode instead of protected or real mode. The alignment check flag is used in conjunction with the AM bit in the CR0 control register to enable alignment checking of memory references. The virtual interrupt flag replicates the IF flag when the processor is operating in virtual mode. The virtual interrupt pending flag is used when the processor is operating in virtual mode to indicate that N interrupt is pending. The ID flag indicates whether the processor supports the CPU ID instruction. In our next tutorial, we will discuss the stack. Part 15, Stack. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Functions are the most fundamental feature in software development. A function allows you to organize code in a logical way to execute a specified task. It is not critical that you understand how functions work at this stage. It is only important that you understand that when we start learning to develop, we want to minimize duplication by using functions that can be called multiple times rather than duplicate code taking up excessive memory. When a program starts to execute a certain contiguous section of memory, it is set aside for the program called the stack. The stack pointer is a register that contains the top of the stack. The stack pointer contains the smallest address. Let's say, for example, 0x00001000, such that any address smaller than that is considered garbage, and any address greater than that is considered valid. The above address is random and is not an absolute where you will find the stack pointer from program to program, as it will vary. Let's look at what the stack looks like from an abstract perspective. The above diagram is what I want you to keep clear in your mind, as that is what is actually happening in memory. The next series of diagrams will show the opposite of what is shown above. You will see the stack growing upward in the below diagrams. However, in reality, it is growing downward from higher memory to lower memory. In the add me example below, the stack pointer, ESP, when examined in memory on a breakpoint on the main function, lists 0xFFFF D050. When the program calls the add me function from the main, ESP is now 0xFFFF D030, which is lower in memory. Therefore, the stack grows downward despite the diagram showing it pointing upward. Just keep in mind, when the arrows below are pointing upward, they are actually pointing to lower memory addresses. The stack bottom is the largest valid address of the stack and is located in the larger address area or top of the memory model. This can be confusing as the stack bottom is higher in memory. The stack grows downward in memory, and it is critical that you understand that now as we go forward. The stack limit is the smallest valid address of the stack. If the stack pointer gets smaller than this, there is a stack overflow which can corrupt a program to allow an attacker to take control of a system. Malware attempts to take advantage of stack overflows. As of recent, there are protections built into modern OSs that attempt to prevent this from happening. There are two operations on the stack, which are push and pop. You can push one or more registers by setting the stack pointer to a smaller value. This is usually done by subtracting 4 times the number of registers to be pushed onto the stack and copying the registers to the stack. You can pop one or more registers by copying the data from the stack to the registers, then to add a value to the stack pointer. This is usually done by adding 4 times the number of registers to be popped on the stack. Let us look at how the stack is used to implement functions. For each function call, there is a section of the stack reserved for the function. This is called the stack frame. Let's look at the C program we created in tutorial 12 and examine what the main function looks like. We see 2 functions here. The first one is the unreachable function, to which will never execute under normal circumstances, and we also see the main function that will always be the first function to be called onto the stack. When we run this program, the stack will look like this. We can see the stack frame for int main void above. It is also referred to as the activation record. A stack frame exists whenever a function has started but yet to complete. For example, inside of the body of the int main void, there is a call to int add me, int a, int b, which takes two arguments, a and b. There needs to be assembly language code in int main void to push the arguments for int add me, int a, int b onto the stack. Let's examine some code. When we compile and run this program, we will see the value of 5 to be printed out like this. Very simply, int main void calls int add me, int a, int b first and will get put on the stack like this. You can see that by placing the arguments on the stack frame for int main void has increased in size. We also reserve space for the return value, which is computed by int add me, int a, int b, and when the function returns, the return value in int main void gets restored and execution continues in int main void until it finishes. Once we get the instructions for int add me, int a, int b, the function may need local variables. So the function needs to push some space on the stack, which would look like int add me, int a, int b can access the arguments passed to it from int main void because the code in int main void places the arguments just as int add me, int a, int b expects it. fp is the frame pointer and points to the location where the stack pointer was just before int add me, int a, int b. Move the stack pointer, or sp for int add me, int a, int b's own local variables. The use of a frame pointer is essential when a function is likely to move the stack pointer several times throughout the course of running the function. The idea is to keep the frame pointer fixed for the duration of int add me, int a, int b's stack frame. In the meantime, the stack pointer can change values. We can use the frame pointer to compute the locations in memory for both arguments as well as local variables. Since it does not move, the computations for those locations should be some fixed offset from the frame pointer. Once it is time to exit int add me, int a, int b, the stack pointer is set to where the frame pointer is, which pops off the int add me, int a, int b stack frame. In sum, the stack is a special region of memory that stores temporary variables created by each function, including main. The stack is a LIFO, which is last in, first out data structure, which is managed and optimized by the CPU closely. Every time a function declares a new variable, it is pushed onto the stack. Every time a function exists, all the variables pushed onto the stack by that function are freed or deleted. Once a stack variable is freed, that region of memory becomes available for other stack variables. The advantage of the stack to store variables is that memory is managed for you. You do not have to allocate memory manually or free it manually. The CPU manages and organizes stack memory very efficiently and is very fast. It is critical that you understand that when a function exits, all of its variables are popped off the stack and lost forever. The stack variables are local. The stack grows and shrinks as functions push and pop local variables. I can see your head spinning around and around. Keep in mind these topics are complicated and will continue to develop in future tutorials. We have been dealing with a lot of confusing topics such as registers, memory, and now the stack and it can be overwhelming. If you ever have any questions, please comment below and I will help you to better understand this framework. In our next tutorial, we will discuss the heap. Part 16, Heap. For a complete table of contents of all the lessons, please click below, as it will give you a brief of each lesson in addition to the topics it will cover. Our next step in the basic malware reverse engineering section focuses on the heap. Keep in mind, the stack grows downward and the heap grows upward. It is very, very important that you understand this concept as we progress forward in our future tutorials. The heap is the region of your computer's memory that is not managed automatically for you and is not as tightly managed by the CPU. It is free-floating region of memory and is larger than the stack allocation of memory. To allocate memory on the heap, you must use malloc or calloc, which are built-in C functions. Once you have allocated memory on the heap, you are responsible for freeing it by using free to deallocate that memory once you don't need it anymore. If you don't do this step, your program will have what is known as a memory leak. That is, memory on the heap will still be set aside and won't be available to other processes that need it. Unlike the stack, the heap does not have size restrictions on variable size. The only thing that would limit the heap is the physical limitations of your computer. Heap memory is slightly slower to be read from and written to because you have to use pointers to access memory on the heap. When we dive into our C tutorial series, we will demonstrate this. Unlike the stack, variables created on the heap are accessible by any function anywhere in your program. Heap variables are essentially global in scope. If you need to allocate a large block of memory for something like a struct or a large array, and you need to keep that variable around for a good duration of the program to which must be accessed globally, then you should choose the heap for this purpose. If you need variables like arrays and structs that can change size dynamically, such as arrays that can grow or shrink as needed, then you will likely need to allocate them on the heap and use dynamic memory allocation functions like malloc, calloc, realloc, and free to manage that memory manually. The next step is to dive into programming C in the Linux environment, where we step by step disassemble each C program. So in effect, you will be learning both C programming and assembly so that you can progress your skills in malware analysis and reverse engineering. I look forward to seeing you all next week when we take a comprehensive step-by-step tutorial on how to install Linux on your current computer using the free VirtualBox software tool.